Hi, good morning, everyone, and thanks for joining us today. This is our first Ask Mayfield Anything, and we are really excited to be doing this. My name is Jennifer Alfson, and I'm joined here this morning with Ryan Mayfield and Rye Heller. Before I introduce them and before we get into everything, I just want to do a few housekeeping things. So if you haven't used this Zoom webinar before, you should have a little menu bar at the bottom of your screen, and you'll see a Q&A. You can submit questions to us live. We are going to answer questions live. So if you think of anything that you want to submit, put them in there, and we'll hopefully get to them later. And any other comments that you want to put in there, feel free. So with that, we are going to be talking about overcurrent protection devices. So Mayfield Renewables does permit level designs for commercial industrial systems. And we also do technical services. So that's something new that we just launched. And by technical services, I mean things like writing white papers, helping with any type of technical content that, say, a product engineer or applications engineer or any technical staff would need to put out to help educate their clients. We can help out with that. And we are really interested in just sharing information and educating the industry, which is why we are doing this. And we're excited to share some of the things that we've learned over the years doing the work that we do. So Ryan Mayfield is our founder and CEO. He has been in the industry for quite some time and has extensive experience. You probably recognize him from the NAPSEP conference. He teaches the all-day NEC training. He also used to be the technical editor for SolarPro Magazine and Home Power Magazine. He did the Code Corner. And thanks for putting this on, Ryan.
Well, yeah, no, thanks to everybody on the team. It's really been a nice effort for everybody. So it's definitely not all me. So glad everybody could make it here.
Yeah. And Rye Heller is one of our senior PV designers. He's also been in the industry for a long time and has been working on commercial industrial designs as well as residential designs. And you also have your a electrical license, right?
Yeah, in the state of Oregon, yes.
Excellent. So welcome this morning, and let's jump into it. So today we're talking about overcurrent protection devices, and Rye actually wrote an article. Let's see if I can get this slide to change. There we go. So if you check out on our website, and I think we're going to put a link in the chat section so you can check that out there. You wrote a blog article about using whether or not you need to use inline overcurrent protection devices when designing a commercial system with solar edge optimizers. So what prompted you to write that article?
Yeah, I think as the industry has moved more towards needing to have module level rapid shutdown, and solar edge has really risen into a product that we're designing with a lot. I found myself really having to research and understand how that system worked, and I was provided an article, well, it was a letter written by Bill Brooks that went into the need for having overcurrent protection if you had 3 strings or more, which was kind of a shocker for me. I was under the impression that the solar edge system would shut down if it had a fault. It's got an IMI circuit built into the inverter's isolation monitor interrupter. And so if it sees any leakage to ground, it's going to trip right away. And so that was kind of a news flash for me, and I started looking into it, and the more I looked into it, the more I realized there was to know. And so writing this blog was an opportunity for me to really dive into it and do some research.
Excellent. So it seems to be a common thing that occurs is, you know, lack of resources or lack of easy to find information that you need. So I'm glad that you are sharing that. So what tips do you have for a designer who's going to be using SolarEdge optimizers and trying to figure out, you know, OCPD?
Sure. I think as the blog goes into really where the focus is where we have inverters that can take 3 strings, or like the large 66 or 100 kilowatt inverter or 43.2. They can take 9 strings, but it's really 3 strings per unit. And anytime that happens, there's the possibility for if one string goes to faults to ground, then you have the possibility of 2 strings backfeeding that 1 string. And so in that circumstance, even though the optimizers are rated to, they won't have any backfeed, they will protect the modules on that side of the circuit, and they will protect themselves and the optimizer, you know, the whips that jump in between. Even though those are protected, the home run wires have the opportunity to see higher current. And so if there's 3 strings, then you need to consider, do I upsize my wire or do I protect that wire? And that's following the NEC guidelines. It may not be necessary, but as far as the code book language is written, you do need to do that.
Mm-hmm. In order to adhere to code, and in case an inspector pushes on that.
Sure.
Right, and so this is getting into the 690.9 exception is kind of the big thing to be looking at here. And so for people who have been doing designs for a long time, this is something, you know, we've had this unofficial 3-string rule or 2-string rule, I guess depends on how you want to say it. But if you had only 1 or 2 strings of modules, overcurrent protection is not required. When you add the 3rd one, most of the time it would be required. There are exceptions to that rule. But that's where this was all really born out of, I think, is kind of the way to step back to. And I think, as Ryan mentioned, with the power optimizers in the circuit, it was a little bit of an eye-opener of, you know, reading and getting information from manufacturers and putting in overcurrent protection or upsizing the wire, because the code exception just says that the conductors have to be sized to accept all of the potential overcurrent. And so when you have multiple circuits in parallel, you could upsize the wire, and that would be a way of making sure that the conductors are have proper protection.
Yeah, and so that could maybe go even further into more strings than 3 even in the future, as long as you upsize the wire to handle the possible fault current.
So right, the kind of the big takeaways then were, if I remember right, so you can upsize the wire from traditional 12 or 10 gauge or putting in overcurrent protection, right?
Yeah, yeah. You either have to upsize the wire to meet the possible short circuit current value that one of those wires could see, or you need to come up with an overcurrent protection method. And with those larger SolarEdge inverters, they do not offer an integrated fuse holder kit. So that really is on the installer to figure out, designer and installer. So a lot of what we're seeing is bumping the wire up to 8 gauge works. It can really help for voltage drop on bigger systems. But it also does have some inherent issues with your conduit size gets a lot bigger, or can get bigger quicker. And when you do the math, you're actually limited to how many wires you can have in the conduit with all the D rates. I've typically been seeing a max of 6 wires in the conduit in order to stay above that 36-inch threshold, which with conditions of use.
Excellent. Well, if you're interested in learning more about that specific application using SolarEdge optimizers, check out Rye's blog. And on the same topic of OCPDs, we got a number of questions in from people who submitted ahead of time. And the first one is about NEC table 250.122 covers equipment grounding, and it says that they are to be sized based on the rating of an OCPD in the circuit ahead of the equipment. So the question is, how does one determine the equipment grounding conductor size for circuits without an OCPD? And they're specifically wondering about a PV source and output circuits to an unfused inverter input terminals. Is there an assumed OCPD rating based on the PV module max fuse rating?
Yeah, so 69045 goes over this. And basically, if you don't need fusing, you have to still do the calculation and come up with a theoretical overcurrent protection size and base it off of that. That math is basically the Imax, which is the IMP or ISC times 125%. And then you have to add in another 125% to get your value.
All right.
So yes, and then you're gonna, yeah, as I said, the table 250.122, and it's interesting to note for those, probably California specifically, having just moved, well, not just, we're already at the end of August, beginning of this year moved over into 2017 code. There was a change in that language as far as how to do that calculation. So it is, like I said, it's based on the 690.9 paragraph B, which says that you have to upsize from the maximum circuit value. So you have to do that 125% twice to get that assumed overcurrent device. Then jump over to table 250.122, and then that's going to be your conductor size. Really where we see this is on smaller systems. It kind of goes right back into what we opened up with and talking about the 3 strings or less. You're typically only going to see non-fused source circuits when you only have 1 or 2 strings on an input, which typically are relative smaller systems. So almost universally what's going to end up happening is your equipment grounding conductor is going to become the same size as your current carrying conductor per table 250.122 on the small conductors. And so that's generally how it's going to go. I mean, it's not always, but that's the typical way that we'll see that.
All right. The next question, and by the way, we are going to be posting the questions in the chat. So if you're wondering like, oh shoot, what reference did I just say, or that was a really long question, we're going to post those in there to help you keep track of what we're talking about. So the next question is, how would you approach the OCPD sizing for PV source circuits on bifacial PV systems without being overly conservative? So do you use a model per 690.8A12? And if so, which modeling software and methodology do you recommend?
So this one's really interesting. Bifacial modules, have become much more popular with, really, I think a big part of it being the financial aspect of it and the tariffs. But regardless, we're seeing a lot more of these bifacial modules. And we've actually been doing a fair amount of research and writing on bifacials as of late. So it's an interesting topic. This specific question is, I would say it's not one that we've done a ton of research on, but the short answer is yes, I would suggest and would look at using that exact code reference 690.8A12, and that's a 2017 reference. And what that's allowing us to do is for systems greater than 100 kilowatts AC, you can do this alternative method. And so it's kind of a key part. There's the greater than 100 kilowatts AC. The code reads 100 kilowatts generating capacity you have to go read what the definition is for generating capacity, but it's essentially the AC output. And then there is a Sandia publication that's referenced in the informational note that goes with that code section. And so that would be the one that, we'll put that in the notes as well. But the Sandia publication would be, one of the ones that I would look at. Using system advisor model is another one that I know people are using to do these calculations. And the really tricky part with bifacial is, the manufacturers give us this whole range of backside boosts that we get from on the bifacial modules, but it really becomes a site-specific thing that you have to do. So,
and it's racking specific too, right? Because it depends on the
yes.
backside shading for that particular racking system.
Exactly. Yeah, it's exactly right. So and so there's a lot more to it than, is it just, what's the backside? Is it, what's the albedo? What's the reflectance? And because you're exactly right, the racking is going to block some of it. What does that racking system look like? And so it's not a super easy answer to say, sure, use the whatever, 15% number or whatever it is, universally, because it is so site specific and so equipment specific. But so it becomes, working with the manufacturers, working with the racking manufacturers, working with whoever your electrical engineer is, because that's the other part of this, is to apply that code section. It has to be done by an electrical engineer. So somebody's going to have to do the modeling, do the math, and be able to stamp it, essentially saying, yes, per my engineering, this is what I expect to see. So I would highly suggest doing that, just because otherwise, if you're going to be ultra conservative, which is kind of will be some people's method, or their default way of going this, and using the highest gain percentage and then applying all of our traditional code D rates on top of that, you're going to be potentially having relatively high overcurrent devices, high conductor sizes for a situation that may not actually come to play. So that would be definitely my recommendation, using either one of those, Sandia or SAM. And then the other interesting part is, I was reading through the code, I was trying to think this through a little bit, and reading through the code, there's really nothing, code just talks about having to apply the maximum current for the short circuit currents, is basically starting with the short circuit current. So it could be argued, the short circuit current traditionally is at STC. So you would have to have some good evidence showing that you're going to get that boost. So it's an interesting question that is definitely going to come into play more and more as we're seeing more and more bifacial.
Yeah, and I know that a number of the racking and module manufacturers are starting to work together to produce additional data around this, because it is so important, especially with calculating performance gains for financial financial aspects. So definitely reach out to the racking manufacturer and the module manufacturers, because I know a number of them have that information, or are at least starting to collect it. So they might be able to help you out. All right, moving on to the next question. What are the changes in 2020 NEC for sizing OCPDs for supply side interconnections?
I can jump in on that one, and Rye, you can back me up hopefully here as we're going. So the 2020 is interesting, because in the 2020 code, we actually have a brand new code section, 705.11, specific for supply side connections. And when it comes down to the specific of this question, it's relatively easy, because nothing's really changed in terms of how we're going to size that overcurrent protection. So what the amperage rating is for that. And what 705.11 does, it pushes us or it points us over to 705.30. Well, the overcurrent protection is in 705.11c, which references 705.30. And in short, 705.30 says you have to have overcurrent protection for all your power sources, and that the rating of the overcurrent protection has to be 125% of your maximum continuous current. Maximum, it says 125% of the maximum circuit defined in 705.28a. This is just a fun exercise in bouncing through code. But in short, what it's saying is that it needs to be 125% of the maximum circuit current. So whatever the continuous output current is listed from the inverter manufacturer, you're going to take that, multiply by 125, and that's going to become your overcurrent device size, or round up to the next size if it doesn't land on an exact size. Now, the question actually kind of begs to go in a little bit deeper, because there are some changes in 2020 specific to our overcurrent device and the equipment that we're using for this overcurrent device, specific to supply side connection. So I did want to take a couple minutes and talk about that, because it is, while the question doesn't specifically ask it, it kind of alludes to it. One of the biggest differences is 705.11b talks about, or requires, that the conductors from the supply side connection to the PV system disconnecting means needs to be a minimum number of 6-gauge copper or 4-gauge aluminum. And it also calls out to install those per 230.30 and 230.43. So you're going to jump back into earlier sections of code, and those are conductor and raceway requirements for service conductors. So this becomes, in my mind, a much more interesting. The whole code section makes it, this new 705.11 makes it easier, I would say, to install supply side connections, because now we actually have some real rules, as opposed to 2014 and before. The supply side connection part of code just basically said, yeah, you can do it, but it didn't tell us how to do it. And then there's another section, and I remember I asked you about this the other day. Yeah. So there's the equipment requirements as well, right?
Yeah, so you're talking about 230.79.
Exactly. Exactly.
So in 230.79, it talks about what your minimum service rating size can be, and it's a little bit confusing. There's some different options in terminology about branch circuits versus service wires. But 230.79d basically says, for all other installations, the service disconnecting means cannot be less than 60 amps. 230.80 also kind of throws a wrench in there, talking about if there's more than one service disconnecting means, then the combined number of switches or circuit breakers can't be less than that value. And so I'm still a little unclear what the minimum really is, but I feel like 60 amps is reasonable.
Yeah, and we've had some jurisdictions that we run across, especially up here in Oregon, where they point to 230.79, and require, basically that's just their requirement, and it's just been the way. And quite honestly, I mean, it's 60 amps, a 60 amp disconnect versus a 30 amp disconnect. It's not
right
that much bigger. It's not that much more expensive. It's and it's a code section that I can see being applied here. So
I think now with the number 6-gauge minimum requirement, it feeds right into that code, and it just makes sense, especially if you're using those type of connections that are biting through the sheathing. I've always felt like it was best practice to at least have a number 6, if not bigger, just for something to bite into.
Sure. And so getting right into that point, 2020 also calls out that those connection points, whatever you want to call it, where you're tapping or you're making that connection to the service conductors, it has that component, that actual physical wiring connection has to be listed for the application, identified and listed for the application of service for being on service conductor. So that's a explicit call out. It's something that I've seen sporadically enforced before, but now it's explicitly called out. And then right along there, with this whole topic, we're talking about 6 gauge versus maybe you can go down to 10 or 8 or something on a smaller supply side connection. 705.11 also gets really detailed into locations of the overcurrent device, how far it can be from that service connection. So, on these smaller ones that we're talking about, you're going to be 10 feet away anyway. So it's not like you're running hundreds of feet and have lots of extra wire costs or anything like that. So all in all, it is more prescriptive. It is more, the supply side connections, they are more defined. But I think all in all, it helps us in the industry.
So I was just going to ask, but I think you already answered it. In terms of affecting, it sounds like this is a rule that will require larger conductors. And how does that affect installation cost? It sounds like it's minimal.
Yeah, I would say minimal because, it's saying 6 gauge minimum, but the reality is...
probably going to use that anyway.
Well, yeah, or the flip side of that is maybe you would have used 10 gauge wire, for example. So going from 10 feet of 10 gauge to 10 feet of 6 gauge. Mm-hmm. Yes, it's more expensive. It's bigger. Your conduit may get bigger, but it's not that much.
Yeah, it's really minimal.
So one last thing I wanted to actually talk about on this point before we leave this topic, and it's answering more than what was asked, which I think for those of you that have been in my code classes, sometimes I tend to do this. We have a slide that we can pull up on this exact point. But one thing that I wanted to talk about, and it was actually, I was just in a town hall with BayWa yesterday, and we talked about this as well. Talked about it with Rebecca Wren, who's on the code making panel, and she reaffirmed a lot of things that I had heard, and she actually sent me some documentation, sent the group some documentation. But a very big question that comes up a lot on supply side connections is, where do I make the neutral to ground bond? And I was smiling because we talk about this a lot.
That's the biggest question.
And it's the biggest question. And up until the 11th hour, it was in the 2020 code. And it got pulled out at the last moment. Long story short on that one, they had almost unanimous consensus on what we're showing on the screen here as being an appropriate method to do it. I won't say it's the only one because I don't know all those codes proceedings perfectly, but the big takeaway was that there would not be a neutral to ground bond in the PV system disconnect. So out of the inverter, you would go to your PV or inverters, go to your PV system disconnect, and that is where you would not have a neutral to ground bond, exactly right there. All of your conductors would go over to your main service disconnect, main service gear. You would make your connection to the supply side conductors. And in that panel is where the neutral to ground bond, it already occurs, and you would leave it there, and that you wouldn't touch it by any means, but that's where that bonding would occur. The one thing that was curious, I thought, interesting about what, talking with Rebecca about this, is ultimately what they came to was that conductor, the grounding conductor from the PV system disconnect to the main panel, they were not calling that an equipment grounding conductor. I believe it was as supply side bonding jumper. which gets into sizing it a little bit different. And that was really, it looks, it feels, it acts like an equipment grounding conductor. They were calling it a supply side grounding jumper, which ultimately means you're probably going to make it a little bit bigger than you would have with an equipment grounding conductor. So
that's what it was called in 2017, or?
No, it's not. Unfortunately, it's not called anything in 2017. It's not called, and it's still not called anything in 2020 because they eliminated that language from the code at the.
So 2023, it might get in there.
Maybe, we'll see. Not having been in that room and not knowing exactly, it sounded, the words that were used to describe it to me was, it was a very political process and very political output. So I'm not going to hold my breath, but maybe it will be there. Nonetheless, I think the good advice is, if you can get if you're having this conversation and it's really difficult, if you're having this as a difficult conversation with an inspector, going and looking at the NFPA records actually might be a good way of showing that this was the way to do it. Otherwise, there's been plenty of times jurisdictions require that neutral to ground bond in that PV system disconnect, and then all of a sudden we're calling that PV system disconnect a service disconnect and treating it as such. So in a lot of ways, we're already doing that. But in my opinion, this is the better way of doing these connections. So yeah, again, taking this question a lot further than it was actually asked, but I thought it was worth bringing up because, like Ryan said, this is the big question. And Ryan, I don't know if you have anything to add in terms of having talked with inspectors or anything on this topic.
Yeah, I mean, this is one of my favorite topics. I've loved coming to you, asking you what you think about this over and over again. But the way you have it shown here is really how I like to do it and how I always want to do it. I feel like it's the simplest, cleanest way to do it. And there's just the theory of having just that single path to ground and not creating a parallel path. Then you get into, okay, now you bond both together. There's been exceptions in the past where you didn't have to bond them together. And so that's a whole other argument to have. And so I feel like this is, obviously you have to take it up with your AHJ, but this method is the fastest way to go and the cleanest way to go.
All right. And if anyone's interested in checking out this image, we could probably post this up on our LinkedIn page and share it.
Yeah. Jennifer, before we leave, I did see that there was a question about this specific. Corey's asking about code reference that requires supply side taps. I think that's what you mean there, to be listed for supply side connections. And it is so it's in 2020 and it's 705.11D. D is in Delta.
All right. So this next question is, what is the NEC reference for OCPD requirements in DC to DC converter source circuits?
Yeah, so I think 690.9 covers that. 699A basically just says that PV system DC circuits shall be protected against overcurrent. And it does provide a couple of exceptions. So this is out of the 2017 code book, but the exceptions are if there's no external sources, like if you just had one string, then you wouldn't need overcurrent protection as long as your wire is sized appropriately. And then the second exception would be if the short circuit current value from all the sources doesn't exceed the ampacity of the conductor, then you also wouldn't need OCPDs. And I definitely got into this in the article about SolarEdge because it's kind of a factor with the with those commercial systems, the optimizer I was using was 18 amps. And so if you have 3 strings, then 2 strings could backfeed one, causing 36 amps to be on a wire. And so if you're running 10 or 12 gauge wire, that would be a problem without overcurrent protection. But that code does talk about needing it. This might be a good chance to talk a little bit about in the article I talked about having an inline fuse option, the MC4 inline fuse option. What that does is it just provides a way to reduce the short circuit current value that the wires would see. Looking into it deeper, the 2017 code book doesn't, it basically just says that the OCPD shall be, that protection shall be at the higher current source connection. So basically at the point of connection at the inverter, but it doesn't really spell it out exactly. And so obviously you can't, you're going to have some wire that's a couple feet long at least from those inline fuse holders to the connection point. 2020 dives in a little deeper even, and it really does make it pretty clear that it should be at the connection point. And so really, even though this is a possible option, it's something you want to take up with your HJ just to clarify the need for that. A combiner panel, on the other hand, once you've combined, then you just have a single output going to the inverter. And so that combiner panel with the overcurrent protection can really be anywhere in the circuit because once you've hit that higher current source, then the single output no longer has that issue.
Right, so I think just kind of keeping in mind that the big idea here is that we're protecting the conductors at the source of where the overcurrent can happen, and that overcurrent can happen where you're putting them in parallel. And so with the rules being the way they are, we want to try and get those, if you're going to use the inline fuse holders that we talked about, that Rye talks about in the article, you can use those. You want to get those as close to the point of parallel as possible, because that's where the potential for faults and faults are going to be in the conductors, where it could overcurrent, have more ampacity on the conductors than they're rated for. So I think that's, and what we were looking at it and, kind of trying to figure out what's the best answer. And it's, it seems like it's a really low risk, not a zero risk, but it's a very low risk situation. And by putting them as close to that point as possible, I think you're doing, definitely trying to protect those conductors as best you possibly can, short of an inline fuse or a fuse holder built into a combiner box or an inverter.
All right. So one idea I had about that, if you've checked out those inline fuse holders, it's basically an MC4 connector on both ends. So you would just plug into it and then leave it. And so I was thinking, well, you could put that in right near the inverter in either a gutter or wire trough, and then so that wire from the PV output or the PV source circuit down could be number 10 into that, but then you could have a short whip of number 8 that would not be, it's on the output side of the fuse going up into the inverter. And so that could maybe solve that issue and keep that a viable option if there is an issue with the HJ.
So that code reference for OCPD requirements in DC to DC converter source circuits, again, was NEC 690.9A.
Yes.
All right. And we're going to move on to the next question, which touches on temperature, selecting what the appropriate temperature to use. So the industry standard for site temperature data can be a lot of times 2% ASHRAE. High temperature is the most commonly used. Some places require you to use the 0.4% ASHRAE high temperature. I know the ETO requires that on a number of things. And then there's also the highest temperature ever recorded, which would be the most conservative calculation. So for sizing OCPD equipment and doing calculations associated with OCPD equipment, which design temperature would you use? 2%, 0.4%, or the max extreme?
Well, we stick with, and I would recommend using the 2% value, and that's that stays consistent with what I would say industry standards are for doing these calculations. And there were some other questions about some temperature stuff that this leads into quite nicely, so we'll talk about those as well. But of course, the interior boxes, things like that, can and will get much hotter than that 2% value. But using my recommendation, and Raya, I don't know if you have anything different to say about this, but using the 2% as kind of that baseline for that value. And I think it might be worth, just in case there's some folks out there that aren't familiar with ASHRAE and these values, American Society of Heating, Refrigeration, and Air Conditioning Engineers, I forget what that last A is.
Yeah, you got it.
All right. That's right up there with NABCET being like just too long of a acronym for me to remember everything all the time.
Yeah.
But they have these temperatures, and without spending too much time digging into it, but the 2% value is the temperature at which it's an average over the summertime temperatures, and the value they give it in terms of degrees C, and what it's saying is that there's only 2% of the time out of those months, I believe it's June, July, August, that ever exceed that temperature. So 98% of the time, it never gets hotter than, and we're talking about number of hours. They're looking at it in terms of number of hours per that period, not days or anything like that, but just hours. So 98% of the time, you're not going to see temperatures hotter than that. The 0.4%, a little more conservative, it's 99.6% of the time. And then, of course, the mention of the extreme high temperature. So short answer, 2%.
Yeah, I concur with that. I feel like 2% is the way to go. And typically when we're designing, that's the number we're running with. When we have to dive deeper, if the OCPD is located inside a conditioned space that is less than that, then that could be a safe temperature to use, more of a conditioned space temperature. But the 2% is, if you can make your calcs work with that, then that's just the way to go.
Okay. And I put a link to the ASHRAE site on weather data in the chat, but you can also access ASHRAE weather data or temperature data for free on the Solar ABC's website. So I put a link to that there as well. All right, so next question. How do you determine the equipment operation temperature for equipment to be installed in the field in direct sunlight for equipment derate purposes? The IE thermal mag trip breakers.
Right. So this question feeds pretty well into, or is fed from that previous question about the temperatures. And so this one, we are seeing quite a bit more, especially as O&M operations become people are much more diligent about their O&M operations, I guess I could say it. And so there's not a great answer that I have. There is a code reference, and I was digging around for it, so maybe one of our attendees can help me out here, because I've just totally missed it. But there is a code reference talking about if your overcurrent devices are in a temperature greater than 40 degrees C, which is 104 degrees Fahrenheit, that you would use their temperature their temperature curves to determine the overcurrent ratings of those devices. So that would be, in my opinion, one of the best ways to do this. And it is something we've seen in the field. And so I've seen some people, talk to some people about doing some modeling. I don't have great references for doing, really good solid modeling on the temperatures, specifically the interior temperatures of the gear. And another really hard part of this is, where we're seeing this is typically larger scale, even ground mount systems, where you have a number of inverter outputs coming in and getting combined into a single enclosure, into a single switchboard. And what we've seen is the temperature, the ambient temperature builds up, hopefully obviously inside that, but then there's all of those inverters operating the current is going to be additive into that heat. And so those thermal mag trip breakers, you may have issues. And I remember one specific site where there was a second AC aggregation panel that fed a second one. And there were a number of individuals inverter breakers on the bottom of this panel, and then this large combined one at the top. And the large combined one at the top actually was tripping due to all the heat that was being built up. So unfortunately, I don't have a great, here's your perfect answer for this, but doing some sort of modeling, doing some sort of, trying to figure out what those temperatures are. Part of the really hard part is it's going to be variable. How hard are those inverters being run? For how long are they putting out the full current? If it's a 1.5 to 1 inverter loading ratio, then they're going to be operating probably, 9, 10 o'clock in the morning, they're going to be putting out full output current. And then by noon, when it's, warm, really warm, or 2, 3 o'clock in the afternoon, those breakers are going to be really hot. So, the comment was in there about, shade structures don't do a whole lot. And it's variable at best. One of the things that I have seen, and I don't have a great answer in terms of here's your modeling and here's how you can figure this out. But one of the issues could be the wire type that you're using as well. So aluminum wire is going to have it has less conductive properties. It's not as conductive as copper, but it's also retains the heat more. And so copper actually will dissipate heat a little bit better. And so using copper versus aluminum may be one of the ways of looking at this, because you have a better current carrying capability and then the heat dissipation as well. So this becomes quite a nonlinear, non-direct equation that you have to run, taking numerous things into account. And so unfortunately, sorry, I don't have here's your perfect answer. But it's definitely something to take into account. And there are some modeling programs, some of the higher end modeling programs that can help take those temperatures into account. Rye, have you seen any of these come up? I know that there was
yeah, I'm not familiar with the modeling end of it, but I have seen the issue come up just with when we've got a PV switchboard with a lot of circuit breakers coming into it. We're worried about how much heat buildup. And so one thing we've done is just bumped the breaker size up a size, which does mean you're bumping the wire size up to make sure it's good for that higher rating.
Yeah, I've seen that too. And the one caveat with that is making sure that the inverter manufacturer, you're still properly protecting the inverter.
Right.
But I've seen that, and I won't say most, but a number of inverters do have that ability, but it's a matter of their listing.
Right.
So that is kind of the quote unquote easy answer, as long as the inverter, you're still properly protecting the inverter for sure.
All right. What sort of modeling programs do you know off the top of your head of which ones include the You're talking about like site temperature specifically for equipment, because
I'd have to, I'm sorry, I should have looked this up before I can post something on LinkedIn or post something on our site or as part of our response. I'm
Okay.
blanking on their names right now.
Yeah, I would think that that would be super valuable, considering, I mean, they do that for modules, right? Testing the modules in standard test conditions and then figuring out a temperature coefficient of how it's going to perform.
Yeah, and the breakers have those as well. So they have the temperature curve that the breakers will definitely have as well. Big trick is what's really going to be the temperature on that breaker, July 21st in, Palmdale, California, after the inverter's been running for 4 hours kind of thing. That's the super tricky part.
Yeah, the actual specific site conditions.
Yeah.
Yeah, it's
all right.
a combination of modeling the solar and modeling the breaker in combination with that.
Yeah. So the next question we have is for large-scale PV plants. Can fuse sizing be optimized by using time current curves versus the standard 125% continuous factor? And what are the implications of such an approach for fuse design life and protection? And then lastly, where did this 125% continuous current factor come from? A three-part question.
Yeah. Let's see if we can get through this. I think we'll make it. Okay. So first part of that, can we use basically can we calculate currents differently? And I talked about this earlier. And so so on systems greater than 100 kilowatts generating capacity, you can 690.A12, and this is 2017 reference. It's there in 2020 as well. You can do a different calculation method to calculate the current value. So I would highly recommend doing that, just because it's going to ultimately, if you're doing site-specific stuff, more than likely, I can't say this with absolute definitive answers, but almost always it's going to result in smaller ampacities and smaller wire sizes. And smaller fuse sizes, kind of the topic that we're talking about. Well, potentially smaller fuse sizes. So definitely I would say doing that makes a lot of sense. And the question of implications, design life and protection, I personally don't have any qualms about that. I think that if you're doing the modeling right, and if you're looking at your site specifics right, that the design life, the protection, design life of the equipment is going to be just fine. It's not like you're overloading anything. And so that leads into this, where did the 125% come from? And so the reason, I'd say I don't really have any qualms about this is we're already so oversizing our wires, so oversizing our overcurrent protection with what I'll call our standard calculation methods, that it's almost a little silly sometimes. So the question talks about the continuous current factor, and I'll back it up a little bit because there is a maximum current that uses 125% as well. That's in 690.8. And so in, what I'll quote unquote our old way of doing these calculations, that we would take the short circuit current times 125%, and that would give us what's defined in code as our maximum circuit current. And that is, so it's ISE times 1.25. And really that's there because PV modules the current output of PV modules is directly proportional to how bright the sun is. And so we have situations where we will have greater than 100,000 watts per square meter, which is standard test conditions. So you're up in the mountains of Colorado, you're on a white roof, you have reflectance, different reasons will give you higher than 1,000 watts per square meter edge cloud effect. And so this first 125% is for exactly that. And then the second 125%, which I think the question is directly referring to, the continuous current, that is 690.9. Now I'm questioning myself as soon as I say that out loud. I believe that's 690.9. All PV circuits, PV system circuits, so both AC and DC are considered continuous. And this is one earlier in code. If you have a continuous current on your conductors, you have to multiply all of your equipment. You would multiply your output current by 125%, and that makes sure that you are not running your conductors and equipment at more than 80% of what their rating is. 80% being the inverse of 125%. So that's kind of the backstory on the 125% numbers. I don't know, Ryan, did I miss anything there?
No, I think you got it. It's so 690.9B talks about the overcurrent device rating, where you have to look back, and in 690.8A, you're doing what you said, which is you're taking ISC times 125%, which accounts for that edge of cloud effect, or, you know, going over the irradiance value that it was rated at. And then in 699B, you would then take that value, the IMAX value, and multiply it by another 125% to get to your wire size or overcurrent protection.
And that's that magical 156% that people like to, in the industry, like to talk about. So 1.25 times 1.25 is 1.56.
All right. Well, thank you both for all of your answers. And if you asked a question and didn't get it answered in this session, definitely reach out to us, technical@mayfield.energy, which is the email you see here up on the screen. And we're going to be doing this again monthly. So we'll have different topics. The next one is going to be on 2% DC voltage drop. So is 2% actually a rule? Is it in code? Where did that come from? Do you really have to use 2% when designing for voltage drop? So let us know what your questions are. We're going to be putting out a blog post shortly about that. It should be published probably early next week. And yeah, submit your questions to us. You can go on our LinkedIn page and find links to submit your questions. If you're not already on our newsletter, sign up for that, because that's where we are sharing what content we're putting out. Thanks so much for joining us, and thanks again, Ryan and Rye. I look forward to our next conversation.
Yeah, thanks so much. Thanks everyone for tuning in.
Yeah, thanks everyone. Really appreciate it.
All right.